Let's study about the charging of a parallel plate capacitor. Here you can see in this picture there is a parallel plate capacitor with plates X and Y which are connected via battery of potential difference V. The battery will maintain a potential difference across the plates as soon as we close the switch. Here, if we close the switch, the positive terminal of battery which is connected to the plate X will start pulling electrons from the plate and will transfer these electrons to the plate Y of the capacitor. And as the charges on the capacitor plates will be equal and opposite, because on X charges will appear, positive charges will appear due to the loss of electrons. And as these electrons are transferred by the battery to the plate Y, an equal negative charge will appear on the plate Y, and we can directly state these charges will reside only on the inner surfaces of the plates X and Y, and the outer surfaces will not carry any charge because the overall charge of the system of this parallel plate capacitor is 0. And in this situation, as the charges are accumulated on plate X and Y, gradually here you can see that electric field is also increasing between the plates, and continuously the electric field will increase till the potential difference between plate X and Y, which here we can write as Vx minus Vy is equals to Ed, because between two large parallel plates electric field is uniform, and as the plate separation is d, the potential difference is Ed. And as E is increasing, potential difference is increasing, and as soon as this will be equal to the battery potential difference, further flow of charges will stop. And here you can say, as soon as the potential difference across the capacitor and that of battery becomes equal, no more further charge flow will take place and the current in the circuit becomes 0. This situation, when the capacitor is charged, one plate, here you can say the plate X is charged with the potential difference V with respect to the other plate, or Y is charged with a potential difference V less than the plate X, then this Qx can be written as CV, and charge on plate Y can be written as minus CV, because here plate X is positively charged and Y is negatively charged. And in this situation, we can say the charge of capacitor is of magnitude CV. And this situation we call a steady state. So here you can write, after steady state is reached, charge on capacitor can be written as CV. Here we talk only about the magnitude, but whenever we say about the charge of capacitor, it implies a charge on one plate inner surface will be plus CV, and charge on the other plate inner surface will be minus CV. And here we can always state that electric field between these plates is, this electric field can always be written as V by D, and that is in a steady state, and no more further flow of charge takes place as soon as the potential difference across capacitor becomes V. In continuation of the discussion of charging of a capacitor, we can also write down a note that whenever a parallel plate capacitor is connected across a battery of constant EMF, or generally we say a battery is a source of constant potential difference, always in final steady state charges on the inner faces of the capacitor plates will become, this will be equal to CV in magnitude. Obviously on one plate it will be plus CV, and on the other plate it will be minus CV. That means if we talk about two situations, say we are given with a capacitor with capacitance C, and it is initially uncharged. And the situation, if we connect it across a battery, it is a similar situation we have seen on the previous sheet. The battery is of a potential difference V. If we close down the switch, it transfers electron from one surface to another, and due to transfer of electron, this plate will become positively charged and this will be minus charged, negatively charged, and finally we can say the magnitude of charge will be CV. And say if we consider another situation in which we are given with a capacitor which is already having some charge on the inner faces of the capacitor, and always remember whenever you are given that a capacitor is charged initially, this automatically implies whenever a capacitor is charged initially, that means its two plates are carrying equal and opposite charges which will reside only on the inner surface of the capacitor. So these charges are plus Q0 and minus Q0. And if we connect it across a battery along with a switch in the similar situation, and the battery potential difference is V. Now if we close down the switch, here again the battery will have a tendency to maintain a potential difference across the capacitor equal to V, because if we talk about the initial potential difference across capacitor, it will be Q0 by C. That we know the charge on capacitor plate is written as CV. So initial potential difference across the capacitor due to its initial charge can be written as Q0 by C. If VIC is more than the battery voltage, charge will flow from capacitor to the battery, or you can say it will discharge. And if V is more than VIC, charge will be supplied by the battery to the plates and its charge will further increase. And we can say this will finally become plus QF and minus QF. And we can say this Q0 will be modified to QF, which is equals to CV. The final charge on the capacitor plates after connecting with the battery will be equal to CV, because capacitor has to maintain the potential difference which is connected across it. So its electric field inside will also get modified in a way that the final potential difference across the capacitor plates will be equal to that of the battery. So always remember, whenever a capacitor is charged or uncharged, if it is connected across a battery of constant potential difference V, final charge on the capacitor plates will be modified in a way that finally in a steady state it will be CV.